Hey guys, welcome to homework up 17. I'm going to share the problems now so we can look at them really quick. So this is homework number 17. So I have the first problem here. Focus on concept. Question 15 says, a source emits sound uniformly in all directions. There are no reflections of sound. So if it's uniformly in all directions, so it's going to be like a spherical shape. At a distance of 12 meters from the source, the intensity of the sound is that. What is the total sound power emitted by the source? So this problem is the same as the next problem. So I'm just going to solve the next problem. So we are given the, what is it called? The intensity, and we are given the distance from the source. This time is a siren for chapter 16, problem 53. So the intensity is power over the area. For a spherical source is 4 pi r squared. If it's a circular source, it's just pi r squared. So we're going to use the spherical source for the power of our area. From here, we have power equals area 4 pi r squared. That is the surface area of a sphere times the intensity you are given. So you're going to use this distance to be your r. So you're going to be 4 pi. Is that okay? 3.49 squared, then times your intensity, 3.85 times 10 to the power negative 2. So when you do that, you just get your power. Exactly the same thing you do here. Put 12 as your r squared, and then 2.7 times 10 to the power negative 3 at your intensity, and solve for power the same way. You're going to get 4.9 watts for question 15. So that's for question 15. And this is chapter 16, problem 53. Intensity is power divided by area. You are given the intensity in watt per meter squared, and you are given the radius, the distance from the source, spherical, becomes your radius in a sphere. The source is going all directions. Then you're now going to use that to compute your power in watts. Okay. So let's go to the next one, chapter 16, problem 69. It says the bellow of a territorial bull hippopotamus is measured at 103 decibel above the threshold of hearing. What is the sound intensity? So the threshold of human hearing is the constant 1 times 10 to the power negative 12 watt per meter squared. That's the I naught. So we are given 103 decibel and they're asking us to find the intensity. Is that okay? So 103 equals 10 log I over I naught. So we know what I naught is. So 103 divided by 10 is 10.3. So I over I naught becomes 10 because it's log to base 10. So it's 10 to the power of 10.3. So I becomes I naught times 10 to the power of 10.3. And I naught is given to be this guy. And you just multiply both of them, we get that as your intensity. Okay. This is similar to what we did in the last recitation. Next problem is chapter 16, problem 76. It says a bird is flying directly toward a stationary bird watcher and emits a frequency of 1460 hertz. The bird watcher, however, hears a frequency of 1530 hertz. So observed frequency is 1530. Source frequency is 1460. So F sub 0 is F observed, FO, and F sub S is F of the source, 1460. So the bird, what is the speed of the bird expressed as a percentage of the speed of sound? So it's coming towards the bird watcher. So it's approaching. So the bird watcher, that's why the bird watcher is hearing a sound louder. So for louder, we have this formula from the from the equation that we have for solving when you have the frequency coming towards you or going away from you. Is that okay? Now, when we do this, we're going to have 1 over 1 minus V source over V. If it was going away from you, then you're going to hear a lesser frequency than the source frequency. Then this here is going to be 1 plus. Is that okay? Here's going to be 1 plus in this equation. Okay. Now, 1 minus Vs over V, they want us to get Vs over V as a percentage. So we're looking for Vs over V given F observed and F source. So we're going to look for Vs over V. So F observed over F source is 1 over 1 minus Vs over V, or F source over F observed is 1 minus Vs over V. And then we just take the inverse over 1. And then from here, Vs over V becomes 1 minus Fs over F naught. So we just put F source 1460, F observed 1530. We get it in fractions, multiply by 100, you get it in percentage. That becomes the percentage, okay? Okay. The next question says, Dolphins emit clicks of sound for communication. Chapter 16, problem 78. Okay, and echolocation. A marine biologist is monitoring a dolphin swimming in seawater where the speed of sound is 1525. Is that okay? 1525 meters per second. When the dolphin is swimming directly away at 6.2 meters per second, the marine biologist measures the number of clicks occurring per second to be at a frequency of 2030 hertz. So it's moving away. So he's going to hear a lower frequency. So that's how we have a plus here for the same one. Okay. Okay. So they're asking us to find the difference between the source and observed frequency. So we are looking for F source minus F observed. So this is F source. F source is F observed times 1 plus Vs over V from here, this Fs over. So we are doing F source, which is this, minus F observed. So we're going to bring out F observed, 1 plus Vs minus 1. So it's just F observed times Vs over V. That's all. And we are given Vs and we are given V. So it's going to be 6.2 divided by 15.25 times 2030 hertz as the F observed, the frequency observed by the one who's monitoring the dolphins. Okay. Okay. So that's how you get this result right here. So now I'll go straight to the next problem. Focus on concept question 08. It says two musicians are comparing their trombones. The first produces a tone that is known to be 438 hertz. When the two trombones play together, they produce 6 beats every 2 seconds. So this is easy again, like the recitation we did. 6 beats every 2 seconds means 3 beats per second, 6 divided by 2. So that 3 beats per second, for you to know the other frequency, add that to the frequency you have or subtract that to the frequency you have, that will be your second frequency. It has to be either of that, of both. So 3 beats per second. So it's going to be 438 plus 3 or 438 minus 3. So 438 plus 3 will be 441. 438 minus 3 will be 435. So we'll have 435 and 441. So the correct answer is B. Okay, that's why the correct answer is B. So it's either the number of beats per second plus the first frequency or the first frequency minus the number of beats per second. So the correct answer here is B. Okay, let's go to the next one. Focus on concept question 04. It says two cellists, one seated directly behind the other in an orchestra, played the same 220 hertz note for the conductor, who is directly in front of them. So what is the smallest non-zero separation that produces constructive interference? So they are playing in phase. So when they are playing in phase, then the distance we can have for you to hear a loud sound has to be an integer multiple of the wavelength. So the first thing to do is calculate the wavelength. So V is F lambda, lambda is V over F. The V is given 343 for sound, frequency 220 hertz. So 1.56 is our lambda. So every 1 times 1.56, 2 times 1.56, 3 times 1.56, every integer multiple of this, I will hear a loud sound. But they're asking us for the smallest one. So it's just going to be the 1 times 1.56, which is 1.56. That's how you get 1.56 meters. So that's going to be the smallest distance, okay? Next, say sound of a certain wavelength is coming from within a room and passing through rectangular door slit. So single slit, the first minimum is lambda over D. And we are told that lambda, the D is twice lambda. So I'll go to put lambda over twice lambda, 0.5. So sine inverse of 0.5 gives me my theta. And that's how we get 30 degrees for this guy. Okay, 30 degrees for this guy. So this angle here is theta. Right here, the same angle here as theta. Okay, now we'll go to the next problem. Chapter 17, problem 08. Excuse me, this is actually the last problem for the homework. So suppose the two speakers in the figure below are separated by 2.5 meters. Okay, so we'll have 2.5 meters from here to here. And then they are vibrating exactly out of phase. So be careful. When they were vibrating in phase, the separation between one speaker and the other speaker, the difference. So what I'm going to do is I'll find the distance from one speaker to this guy and the distance of the second speaker to this guy. Find the difference. If the difference is a multiple of the wavelength, so we first of all find the wavelength here, which is 343 divided by the frequency 429, 0.8. So if the difference between these distances is a multiple of the wavelength, if they are vibrating in phase, I will hear a loud sound. It will be constructive interference. But if they are vibrating out of phase, an integer multiple becomes destructive interference. So be careful, okay? So it is half integer that becomes constructive. That's why we hear a loud sound if they are vibrating out of phase. Now they are vibrating out of phase, so I'm looking for the one that is half integer of the wavelength, 0.8. So now let's go there. So 1.15 meters is from C to B. So let's find A to C. 2.5 here, 1.15 here. So we're going to take this square plus this square and take the square root to get this guy, and then get the difference between this guy to this guy and B to that guy. So I have it here. So del D, that distance is DAC from A to C minus DBC from B to C. So DAC is AB plus BC squared square root, okay? That's A to C, then minus DBC. So if I use 1.15 meters for the first part of the problem from B to C, I do it here. So I'm going to have 2.5 square plus 1.15 square root minus 1.15. That gives me 1.6. 1.6 is exactly twice the wavelength, 0.8. So it's going to be destructive interference. So because they are vibrating out of phase. If they were vibrating in phase, this answer would be constructive interference. Now, if BC is 2 meters, so I'll calculate my difference again in parts from B to C and from A to C. So the difference becomes A to C square root of AB squared plus BC squared minus this distance to get the path difference. I do that again, I get 1.2, and 1.2 is exactly 1.5 of lambda. So I'll hear a loud sound there because they are vibrating out of phase, okay? Because they are vibrating out of phase. So take time, look at these problems again, see how they are solved, and look carefully. I might be a little fast going through them because you've done this in class, but take your time, slow down, look at the solutions again, and you should be able to grasp this. Thank you so much and see you next week.